Thank you very much for the introduction. What I'm going to spend a bit of time talking about this afternoon is some of the work we've been doing with some of the single-wall carbon nanotube materials that we've collected from Oxiol, and exploring ways in which we can actually make them into better performing cathode materials for battery systems. So of course, there's many different battery systems out there that can be used. Our main focus here today is on the alkaline manganese dioxide cathode. Of course, this can also be, the technologies can be extended further to go to other different cathode systems. But nonetheless, we're going to start here with this type of material to see what it can be done and how it can be used and how we can improve its performance with the inclusion of these types of carbon nanotubes. I do have quite a few background slides here, but I'll go through them quite quickly. One thing that we all know is that energy is a very important aspect of future society. That reliable, sustainable production of energy is critical. And so there needs to be a whole range of new technologies to actually try and make that a realisable fact. Of course, in terms of energy generation, we also need ways to store energy as well. And so there are, of course, many ways in which we can actually do that as well, whether it be through things like kinetic energy, electrical energy in capacitors, which is something we do a lot of work with, solar photovoltaics as well. They can actually be used to store energy, chemical energy as well, solar thermal, nuclear processes as well. They can also be used quite a lot. But what we're interested in here is energy storage, which plays a key part in actually being able to produce that energy-related, sustainable energy production. And so our main interest here is in the electrochemical forms of energy storage, those being things like fuel cells, battery systems, capacitors, and electrochemical capacitors, and also electrolytic capacitors as well. And so the example we're going to consider here today is to do with the battery systems, such as you see here, lithium-ion and also alkaline battery systems. Right, so that's where we come about being able to then try and use these carbon nanotube materials in these particular systems. And of course, there's many different battery systems I alluded to before, whether they be primary systems, secondary systems, and a whole range of different chemistries as well that can actually be used in these type of devices. And so the question becomes is that how can each of these types of systems be actually improved through the use of carbon nanotubes? All right. So one thing that we do need to be aware of when we use a battery system, for example, is that a lot of the active materials that we use are actually semiconducting in nature, particularly on the cathode side of systems. They tend to be semiconducting in nature. And so, of course, what we need to include there is a conductive element. And most often these days it's done with a graphite or a activated carbon or a carbon black material to actually improve the conductivity of these cathode-based systems. Right, and so what it means then is that it becomes a balance. There's a need to have a balance between the active material in the cathode and also the conducting material in the cathode. And so that's where we need to actually optimize that relative amount of conductive element within that system. Right, and so you can see here on the left where you can have too much conductor, not enough conductor, and that will limit your performance. Now, what's critical about this is that we need to maximize the amount of carbon efficiency in our cathode, or conductive efficiency in our cathode. What we need is excellent conduction within the cathode itself. Being a semiconductor material, it can't work by itself, it needs that conductor. But we also have to maximize the amount of active material that's there as well. Unless we get that balance right, then we begin to start to optimize these types of systems. What's critical out of all of it is this three-phase boundary, that interface between our electrolyte, our conductive agent, and the active material. It's at these regions around that three-phase boundary that we actually start to carry out our processes that are involved with the system. All right. So our focus here is on the manganese dioxide, alkaline manganese dioxide electrode. Why do we start there? Well, it's certainly a developed technology. It's been around for many, many years to date. But still, it's a very, very high volume system. And you can see here keep pressing the wrong button. So you can see here in the top right-hand side, basically how the dollar value of the primary alkaline system is continuing to increase with time. The basis of it all on the cathode side is the manganese dioxide, and that's made using electrolytic processes. There's some examples of the structure of the material that we're actually using. This is by far and away the most active form of manganese dioxide to use in an alkaline system. Right, so what's so important about it? How can we actually include carbon nanotubes into this type of system? Well, what we've done is actually, because it's made electrochemically, what we need to do is actually find a way to incorporate those carbon nanotubes actually into the EMD material itself. Right, so that can be done either post-production, just through mixing of carbon nanotubes with the active material, but it can also be done in situ, if you like. What we have here is a way in which we can carry out our electrodeposition process to make manganese dioxide. It can be done electrochemically in the presence of the carbon nanotubes suspended in our plating bath there. And during the plating process then, those carbon nanotubes are essentially embedded into the EMD structure. So really the point about that is that you actually get a much better mixing of your carbon nanotubes with your active material, much more so than you would if you would just mix them post-production. We've also done it chemically using a somewhat similar process. This is a hydrothermal process where we actually mix the carbon nanotubes with the active material and basically co-precipitate the active material around the carbon nanotubes. The important thing about it, the linkage between the synthesis conditions, the structure and performance is a key aspect of the whole process. If we can get the synthesis conditions right, that includes making the manganese dioxide, but also including the carbon nanotubes, then we can certainly go about improving the performance of our system. Okay. Here's just some examples of the inclusion of carbon nanotubes into our various systems. So these are some chemical-based systems, and you can see there evidence for the carbon nanotubes being wholly and solely embedded in amongst the active material in that particular system. We do have some instances here of clustering of the carbon nanotubes to actually make our materials, but nonetheless, we still have a very, very intimate mixture of the active material with the carbon nanotubes in these cases. Okay. And so what we're aiming to do is basically achieve higher conductivity within our cathode and hence achieve a higher material utilisation and ultimately get a better performance out of that system. Okay. So we've done a lot of work actually exploring the inclusion of carbon nanotubes into the manganese dioxide structure, basically an in situ inclusion of them into the structure. And one thing that I really like is this little image down on the bottom right-hand corner here. This is manganese dioxide that's actually been found embedded around a carbon nanotube in that particular system. So it's essentially just a piece of broken manganese dioxide with a carbon nanotube that was actually embedded in the centre of it. So we've found a lot of interesting outcomes from this in this particular case. How does it go in terms of performance? Well, here we're looking at the conductivity of our materials. Looking at the table over on the right-hand side, we can basically go from about a tenfold increase in conductivity with just a very small fraction of carbon nanotubes included in the manganese dioxide structure. So in that regard, it's actually quite promising. We're actually getting a much better mixing of the materials together. Okay. What about in terms of the conductivity, or a couple of other comments about the conductivity of these materials? We've actually looked at these in terms of their percolation threshold to try and determine the optimum amount of material that's actually being included. In that regard, we've actually, you see over here, we have percent carbon additive included versus the log of conductivity. What we see here is that for the starting material, we actually do improve the conductivity, which is great. But still, nonetheless, we still can't move the percolation threshold at this stage from its point for this particular system. So the conclusion there is that while we have intrinsically increased the conductivity of our manganese dioxide, what we haven't done is actually extended those carbon nanotubes that are included to the external conductive network. Right? And that's significant. That's a key feature because when we've done that, we can increase both the intrinsic conductivity of the material as well as lower the percolation threshold that's necessary to make a conductive carbon network through the cathode. And so that's a key challenge for us into the future. Okay. We've also done a lot of work looking at the performance of these phases as well. Again, these have been designed to not only test the intrinsic performance of these materials, but also look at their carbon efficiency when it comes to their utilisation. And so we carry out performance measurements voltammetrically, as you can see here. We can see performances at various cut-off voltages as a function of the fraction of carbon nanotubes that be included in the material. And certainly we can get some much more enhanced performances. That's about a 10% improvement in capacity compared to these the unmodified material there. And that's significant. Even though the alkaline system has been around for a long time, there's still a lot of scope for performance improvements here, particularly under high rate applications. And so that's some of the characteristics we're trying to target. Okay. And then these are, again, some information leading to trying to optimize the amount of carbon included into the material. And really what we're doing here is focusing on carbon efficiency, basically examining the optimum amount of carbon that's necessary for conductivity and for performance, all the while minimizing the amount of inactive conductor within the system. All right. So with that, there's just a couple of key outcomes from our work, mainly associated with the conductivity of these materials and their performance. One final note that I will make as well is that these materials can also be used as precursors for lithium-ion cathode materials. And so with the embedding of the carbon nanotubes into the manganese dioxide phase, we have the capacity to then transform them into lithium-ion materials, like lithium manganese oxide and a range of others, all the while still maintaining that carbon nanotube network within that path. So with that, thank you very much. I'd just like to acknowledge a couple of people, Konstantin and Dimitri, who were involved with us. Hayden, this is part of his PhD studies, and that's Newcastle there, by the seaside. So thank you very much for your attention.
Scott, when you talk about moving that technology over to lithium-ion, what do you expect the improvement to be? Is it energy density? Is it C rate? What do you expect the improvement to be in the lithium-ion system?
I expect it to be in C rate, improved rate performance of these materials. Effectively, with a better conductive network, you have better charge distribution through your particles as well as your cathode, and that would tend towards implying that you're going to get a better rate performance from your materials, or alternatively, a higher efficiency at higher discharge rates.
And how easy would it be to integrate the nanotubes into the process? I mean, does it disperse easily through the electrochemical process?
Yes, we've found with the right dispersant actually being used within the suspension. When we put it into the plating bath, it's suspended, it disperses very easily. The question becomes is how is it included into the manganese dioxide, how it attaches to the MnO2 as it's being deposited down. But as you saw before, in some of the SEM images, there's a good interface between the phases, between the carbon and the MnO2. Then it's processed normally, and then it can be used either as an alkaline cathode or further processing to make a lithium-ion cathode after that.
So once the nanotube is inside the active material, then to the manufacturer of the cell itself, there is no additional processing that would be required.
No, that's correct. That's correct.
That's really interesting. Thank you.
Okay. Yeah, it is. And yeah, one question from my side. Scott, what is your expectation when this technology would be commercialized? What is your, let's say, vision or expectation?
So there's a few. So our focus is mainly on the material side of things.
Sure.
We haven't really examined it from a production point of view. We make materials at the order of about a kilo of material. On the industrial scale, it's made 100,000 tonnes per year of EMD is actually made. So how to include that into the process becomes a key question. What you don't want to lose your carbon nanotubes actually as you're processing the materials, and so that's the key aspect of it as well. But having said that, though, I don't think the challenges are insurmountable. I think it can be accomplished in a relatively straightforward way.
Yeah, so, sounds encouraging. Yeah, thank you so much once again. Thank you.